Hello and welcome to the first presentation for the Mechanics 2 module. We're going to start on the first chapter, which is a model for friction. And we're going to start off as an introduction, and hopefully by the end of the lesson you'll be able to solve this particular problem. The case of the SkyGo versus the Mercedes-Benz. So, here is the SkyGo. A beautiful piece of machinery in the middle of the main square in Marrakesh in Morocco. A bit of a death trap, but one day it got involved in an accident. And this is the police report. Okay, briefly, the circumstances of the accident are that our client was driving his Mercedes-Benz. He had just left work at the end of the day. He was stationary at a junction on a hill of 5 degrees to the horizontal when the SkyGo came down behind him with excessive speed and crashed into the Benz. The SkyGo was braking when he lost control and left a 26-meter skid on the road. Our advice from an expert mathematician is that he was exceeding the speed limit of 30 miles per hour. Okay, so by the end of the lesson, hopefully we can be able to solve this particular problem. Okay, about whether the SkyGo was speeding based on the 26-meter skid using this model of friction. Okay, that's Alvin Toffler. Theories do not have to be right to be useful. Okay, and that's an important case. We're modeling real life here, and in the modeling process, we have to make simplifications. We have to make assumptions, which means that although the theory may not be 100% accurate, it can still be useful for us to get some good results. So, it's called Coulomb's law of friction, and the main principles are this. Friction will always oppose motion. So the frictional force of an object will always oppose the motion of the object or the desired motion of the object. Friction is independent of the speed of the object. Okay, now this is perhaps a bit woolly, but this is in the case of objects on a surface, the contact between two physical surfaces. If we looked at a model of friction, model of air resistance, for instance, then there would be some dependence on velocity. So this isn't really a model for air resistance, it's a model for two objects in contact with each other and the frictional force which they experience. The magnitude of the frictional force has a maximum which depends on the normal reaction between the two surfaces. Okay, so if you've got a box on a surface, the normal reaction of the surface to the box, if we look at that force, it depends on that normal reaction, the size of the frictional force. The bigger that normal reaction, the bigger the frictional force. Now this is where we get into the nitty-gritty. Okay. If there is no sliding motion between the two surfaces, then F, the frictional force, is less than or equal to mu, which is, we call the coefficient of friction, multiplied by R, which is the normal reaction. Okay. When motion is about to occur, the frictional force is said to be limiting, and its value is that F is equal to mu times R. Okay. And this is the key equation. F, the frictional force, is equal to the coefficient of friction multiplied by the resistive force. We do a little brief analysis of this. So if the frictional force is in newtons, the resistance, the normal reaction is in newtons, that means that mu, our coefficient of friction, is dimensionless. It's just a number. Okay? And when there is motion, finally, the frictional force is also equal to mu times the resistive force. Okay? Hopefully this will come clear in the light of a couple of examples. So here's, you don't have to remember these, but if you've got two wood objects, the coefficient would be between 0.2 and 0.6. Metal on wood, 0.15 to 0.3. Racing tyres on the road would be a coefficient of 1. Skis on snow, a coefficient of 0.02. So obviously this kind of suggests that the lower the coefficient of friction, the less friction there is, because obviously skis on snow, you don't want there to be much friction, otherwise the enjoyment of being on some skis going down a slope would be diminished. Sandpaper on sandpaper, however, you want there to be a lot of friction because that smooths the wood or whatever, and so that's got quite a high coefficient of friction of 2. It can't be negative. Can't be negative because friction always opposes motion, but it can be it isn't restricted. It can be positive and it can be any value of positive. Okay. So let's go over an example. Here's the first example. A person tries to pull a small cupboard across the floor. The mass of the cupboard is 80 kilograms and the coefficient of friction is 0.5. Describes, first typo of the day, describe even what happens if the cupboard is pulled with a horizontal force of A, 200 newtons, and B, 400 newtons. Okay, let's get a diagram. Mechanics is all about getting the diagram, getting a feel for the problem, and then we can solve it from there. So I'm going to model the small cupboard by a particle, quite a big particle there, just for the sake of our modeling here. At the minute, we're not going to be worrying about size of the object. We're just going to say it has mass. Okay, so it's going to experience its weight, ATG. There's going to be a normal reaction, and the person's trying to pull it. So there's going to be a pulling force to the right, and there'll be a frictional force to the left. Okay, so that's the setup. Pretty standard. It's on a horizontal floor. We don't have to worry too much. And they're the actual values for the first example. We've got the normal force of 80 grams because there's no vertical motion, so it's balanced by the weight, which is 80 grams, sorry, 80g. And there's a pulling force of 200 newtons. So what happens here? Well, we need to find a value of our limiting friction. Okay, now limiting friction is denoted by mu times r. Now we've got our mu as 0.5. We've got our normal reaction as ATG, so our limiting friction is 0.5 times ATG. Okay, so the limiting friction is 392. Now, what that is saying is that it's not until the frictional force gets to a value of 392 and then motion will occur. Okay, now since 200 newtons is less than 392, there is no motion. Okay, this limiting friction of 392 tells us that I'm not going to be able to do that. This limiting friction of 392 tells us that to make the object move, there has to be a resultant force of, there has to be a force going in the other direction of at least 392 newtons before this object will move. Okay, now so there's no motion because the limiting friction is 392. If we do it for 400 newtons, now 400 newtons it says less there, it's ridiculous. 400 newtons is larger than 392 newtons, so there will be motion, and the resultant force will be 8 newtons because we have the frictional force. The limiting friction is 392. You could imagine this if you like. Let's just get rid of this for the minute. Ignore that 400 newtons. This object, we're trying to push it. Okay, we're trying to push it, and if you imagine the frictional force is going to stop you from pushing it. If you just push it with a tiny force, it's going to stop it from. The friction is going to stop you from being able to move it. When it is on the point of moving, the frictional force will be this. Let's change that. There will be this limit. It will be the value of this limiting friction, which is mu multiplied by the normal reaction. Okay, so we start off pulling it by 0 newtons if you like, and if we keep on pushing it and pushing it and pushing it, when it was 200 newtons, it didn't work. Okay, when it was 200 newtons, we wouldn't have been able to move it. Okay, because the limiting friction tells us that we have to pull it with at least 392 until we get some motion. Okay, at 400 newtons, we overcame that limiting friction of 392. And because we overcame it, 400 newtons is 8 newtons larger than 392, so the resultant force of our motion is 8 newtons. Now we can work out the acceleration there by plugging it into F equals ma, so 8 is equal to ma, so 8 is equal to 80a, or if we work that out, a is 0.1 meters per second. Okay. That should be nothing tricky here, but it's just about getting your head around what this limiting friction means, okay? Let's go over another example. A boy kicks a stone of mass 100 grams across the playground. The coefficient of friction between the stone and the playground is 0.25. If the stone comes to rest 31 meters away, find the speed with which the boy kicked it. Right, let's just set up a diagram. There's our ball. It's 100 grams. It's going to have weight. It's going to have a normal reaction. Now, as it's just been kicked, after it's been kicked, there's only going to be acceleration, and the only force it's going to have is this friction. Now, the friction is going to tell us. It's going to give us, it's what stops it. It's what stops it from moving, basically. It's what causes the deceleration to 0. And there's the values: 0.1 g for the weight, 0.1 g for the normal reaction, and we have the friction over there. So there is motion. So there is limiting friction, which is mu times r. So the size of the frictional force is mu, which is 0.25 times by 0.1 g. Okay, and that is 0.254 newtons. So our resultant force is going to be, well, we've got a frictional force of 0.245 newtons. Now the resultant force is equal to MA, and because it's in the direction opposing motion, it'll be minus 0.2445 is equal to 0.1 A. So working that equation out, A is equal to negative 2.45 meters per second, which tells us there's deceleration. Now, using UVATs now, we know that U is unknown, V, the initial speed, is unknown, which is what I'm trying to find out. V is 0, the final speed is going to be 0 because it comes to rest 31 meters away, and we've got negative 2.45 meters per second as acceleration. So that's going to be the we're going to use, the equation v squared is equal to u squared plus 2as to solve for v. So to solve for u even, plugging all those values in, we get 0 because v squared is 0 is equal to u squared plus 2 lots of minus 2.45 times 31. So rearranging that, not too tricky, that u is equal to square root of 159, which is 12.3 meters per second. Okay, so really it's just getting used to the idea that if there is motion, the frictional force will be its limiting force, which is mu times the normal reaction. If there isn't motion, then the frictional force will be less than its limiting friction, and you have to overcome that limiting friction, mu times the resultant, for it to work, for the motion to kick in, if you like. Okay, hope that's helped.